So this is Manfred Warmuth from my homestead in Santa Cruz. Joint work with Ehsan called Winnowing with Gradient Descent. Okay, there's two main families of updates, the gradient descent family, backprop, Newton's update, kernel methods, and the multiplicative updates, the exponentiated gradient update. Expert algorithm boosting Bayes belongs to that. The unnormalized version, the main example is Winnow. Typically what happens for gradient descent, the regret bounds and the convergence is linear in n, the dimension of the instances. And for the multiplicative updates, it's log n for sparse targets, yeah? Very important. Okay, here we will reparameterize the multiplicative updates as gradient descent, and the reparameterized forms act like the original multiplicative updates. In the continuous case, it will be identical. So in some sense, we winnow with gradient descent. So look here. So assume the instances are rows of a Hadamard matrix. They're orthogonal, right? And the target is one of the columns. So it's a paradigmatic problem where the target is sparse, right? I'm picking out one component. Linear, sparse, linear, okay? Third instance, label is -1. Okay, now I do linear regression. Get one example at a time, one row and one label, right? And I incur square loss, and I do the multiplicative update, which puts the gradients of the loss in the exponent, or an additive update. These are special cases of mirror descent, right? Where the link function is either the log for the multiplicative or the identity for the additive update. Good. So now, if you have the 128-dimensional Hadamard problem, you present random rows, this happens. There's major differences between the updates. The gradient descent update, all 128s plotted in blue here, the good weight is picked up only linearly, and the average loss on all 128 instances goes down only linearly. For the multiplicative updates, fundamentally different, exponential decay, exponential pickup of the good weight. Okay, so the punchline is after seeing half of the examples, you still have error half in the gradient descent case, and whereas for the multiplicative updates, after log and many examples, you learn. There's a lower bound for the multiplicative updates that matches this behavior. And the lower bound says that even if you expand the instances with an arbitrary phi map, then on the average, the linear lower bound remains. It even remains if you have a sigmoid here or a transfer function here, okay? But the bounds are slightly weaker. So we conjectured that the Hadamard problem is hard to learn, and you have the linear lower bound no matter what kind of neural network you pick, as long as you train it with gradient descent. That's false, as we will show today, but we have a refined conjecture. Our argument goes first to the continuous case. So you do f dot equals -8 of the gradient. Okay, and the main updates again are gradient descent and the multiplicative update use the log link. So gradient descent identity link, multiplicative update the log link. And then we discretize, okay? So in the continuous case, the two updates are the same, the additive and the multiplicative. Or we can make them, we can simulate them by each other. So using a trick, using a reparameterization. Okay. So as a side, this implies the conjecture about training gradient descent is false because the discretized version of these updates and its simulations are close enough. We also show that the structure of the neural network determines the regularization, as you will see. So pictorially, what happens is this gives you the lower bound, gradient descent trained on this simple linear neuron. But if you train gradient descent here, then this is the update, which is the same as the multiplicative update on the original. Again, gradient descent on this update, backprop on this update, on this neural network, is the same as multiplicative update on the original. Now you discretize. So here's the discretized versions of these updates. And curiously enough, they act the same. And here's the multiplicative update discretized. So GD, discretized EGU, discretized reparameterized update. And these two act the same. They are numerically not the same though, but they just act the same. Actually, we proved that they have the same regret bounds. Okay. So in particular, there's a simple linear 2-layer neural net that cracks Hadamard. So here's the network. When you train this with gradient descent, with respect to the weights on these double edges, you crack Hadamard. You have this behavior. Even if you add all the weights, you always get, if you initialize them to 0, you get gradient descent again. So the sparseness seems to be necessary. Also true when the bottom weights are initialized to 0. Okay, and this one, the combined weight, converges when you train it with gradient descent to the smallest L1 norm, also observed by many other people, Natis Rebro, Surya Gunasakar, and all these people. Very nice papers. If you add all the weights, then you somehow go to the smallest, something that is close to the smallest L2 norm. Details have to be worked out still. Okay, so what's the punchline? This one, any phi map, linear lower bound. This one, 2-layer neural network, linear neural network, no transfer function, trained with backprop, cracks Hadamard. So this is, in this case, this particular case, this one solves a problem exponentially faster than this one. Okay, major difference. Good. How do I go from continuous updates to discrete updates? Well, I can use Bregman divergence. I can do discretization or use Bregman divergences. Here's the Bregman divergence definition. There's a duality. This is the usual way in which we derive updates in the code community. This is mirror descent. Okay. You get, if you do this direct minimization, you end up with the implicit update, future gradient, but you can approximate it with the old gradient. Okay. Good. So continuous mirror descent is this one. And we also, the multiplicative one was the log link, you see? And now we changed the log to be a log tau and modulate the tau. So this is the original logarithm, tau equals 1. Tau equals 0 becomes straight line gradient descent, as you'll see. Okay, you can motivate the continuous update also using Bregman divergence. You have to do a Bregman momentum. It looks like this. And you do a little bit of variational calculus, and you end up with this update f dot equals minus the gradient. Okay, the continuous mirror descent update. Now, we show if you have a reparameterization function such that mirror descent with the G-link composite loss simulates mirror descent original loss if certain condition holds on the derivatives. Okay, main example. Main example is the original link is log and the G is the identity. Okay, and now you check the derivatives, very simple. And what happens is this shows that log W equals U dot equals minus gradient with respect to the composite loss, which is the original gradient component-wise multiplied by the UI. Okay. You can do this for many mirror descent algorithms. For instance, Borg, continuous Borg, you can do it as gradient descent as well. So now you use as your reparameterization function xpu, and now you have 1 over W minus 1 over W dot, okay, using that link, can be simulated by gradient descent with respect to this composite loss, which is the original gradient multiplied component-wise by exponentials. Kind of curious. We can also interpolate. The log tau update can be interpreted as, can be reparameterized as this gradient descent. So your link function is now log tau of W. Use this Q function and you check your derivatives. And then what that means is that the log tau update equals this gradient descent with respect to this composite loss, which in picture means gradient descent on this neural network where you have these powers now on the UI, simulates the log tau update. When tau equals 0, you get UI a half, which becomes a UI. So that's the linear neuron. When tau equals 1, you get UI twice, which was the multiplicative update simulation. So here are all the updates. Exponentiated gradient unnormalized. I used the hedge loss, dot loss. Unnormalized version of the approximated exponentiated gradient. You get this. And now this is our update. So we work with the square roots of the weights, which are the UI, you see? And if you go back to the original, you have to square them. Hedge update, famous update related to weighted majority. And here's the update. The approximated EG update is this. That was mirror descent with respect to chi squared. Prod update approximates the exponential. That doesn't have a mirror descent interpretation, as far as I know. But our update is very similar to the prod update, but it works on the square roots, and then it squares, and subtle differences. If you look in the original weight domain, it would be this. Okay. Okay. Cold wants regret bounds, so we gave them regret bounds. So the total loss of the update is less than or equal to the total loss of the best comparator plus norms times, this is the kind of bound you want. Okay. So we prove, if you do this simulation, EGU as GD using the squaring trick and hinge loss, you can simulate window in the sense that you prove the same regret bound. For linear regression also, we have the same regret bounds, right? And for EG as GD dot loss, the same as hedge. Okay, so all proofs are done with a relative entropy as a measure of progress, and that's totally surprising. So we don't use the gradient descent measure of progress in our proofs. We are still puzzled by that. Many open problems. We still need to get bounds for EGU and EGU as GD for the two-sided case. We only have it for the one-sided case. And is the natural problem for which gradient descent beats EGU plus minus? We want an elegant problem. We have many, but they're not elegant, as elegant as I want them. And now, since we show that gradient descent is so powerful and can do all kinds of things, including mimicking multiplicative updates, would be important to you revisit all of those issues: vanishing gradient, batch normalization, dropout, learning grade heuristics for neural networks, you see, but do it not with complete connections, but with these sparse neural networks. Large-scale simulations, and the open questions now goes like this: does any gradient descent neural network with complete input neurons, so when a neuron gets an input, it always gets all of them, not just a single one, as in our spindly network, does any gradient descent trained neural network of that type, we conjecture it cannot crack the Hadamard problem. Thank you.